Hello, AP Stats. This is Mr. Kim, and in this video, you will be guided through for the Chapter 2 materials for normal distributions. I would have to say it's probably one of the easiest ones and very short one. And so without any further ado, let's get started here. In the very first question, we have the normal distribution of men and women. We have the mean of 68 and a standard deviation of 3 for men. So if you were to actually just draw this out, we are looking at 71, 65, and then I can just kind of write those down, but you understand that the first thing you have to do is always just draw them out. And then the 65, 2.5 for women. So we have 65, and then we have 67.5, we have 62.5, and then two more standard deviations after that. Which of the following is going to be true? Now, the percentage of women shorter than 62.5 is smaller than the percentage of men shorter than 65. Well, if you take a look at these two locations, I mean, those two are exactly in the first standard deviations to the left. A is not going to be true because they're going to give you the exact same amount in the normal distribution curve. They are higher percentage of women between 62.5 to 67.5, between 65 to 71. That is absolutely not true because they both, by empirical rule, should give you about 68% like this. More than one half of the men are taller than 68 inches, which is true because that's half, while only 1/4 of the women are taller than 67.5. 67.5, that should amount to about 16% doing the math with the empirical rule. So that is not true. Approximately 95% is between 60 to 70. Now, if you were to go one step further, one more standard deviations to left or right, you should be getting 60 to 70 for women, and for 62 to 74, add 3 and subtract 3. Yes, these two numbers are exactly what we're looking for, so that should be D. The percentage of men with heights between 68 to 71, percentage with heights of 65 to 67.5, that shouldn't be 62, that should be 62.5 in order for that to be true. Number 2, which of the following is not a correct statement? So the men's heights have more variation than the women's heights. Yes, because the standard deviation is definitely higher here. We're talking about the not correct statement. The men's height distribution is more skewed than the women's height distribution because the standard deviation for men. Skewness has nothing to do with the standard deviation. It has everything to do with the shape. So B is definitely not the correct statement. On average, men are taller than the woman. That is definitely true because the average is obviously taller. Since the standard deviation of men's height is larger, you would expect the graphical display of height distribution to be more spread out for men than women. Yes, absolutely true. Although more men were sampled, you can still expect about 68%. Yes, that's absolutely true. So B is the complete nonsense here. 150 students have had heights that were roughly normally distributed with a mean of 65, standard deviation of 2.5, 102 students. So what are you going to do with this question is that you're going to take your calculator here and you're going to simply do 102 divided by 150, which kind of gives you the percentile rank. So you're looking at 68th percentile. And so if you remember from the empirical rule, 68% means one standard deviation to left and right. So one standard deviation left and right for this should give you D. So the answer for number 3 should be D for this one. Number 4, a 2 study of high school students, 1980s. We have the mean standard deviations for both male and female, boys and girls. Darnell ran 394 and Christina ran about 500. So when you read this, they ask you to find the z-score, which you should know the formula. It's the value minus the mean over standard deviation. So for Darnell, 394 minus 460 over 55, that should give you negative 1.2. And for Christina, it was 500 minus 591 over what was the standard deviation? 70, which should give you negative 1.3. So those two are the respective z-scores. Now, if the z-score is negative, it means that the further you're away from the standard normal distribution with the mean of 0 and a standard deviation of 1, it means that the further you're away from 0, you have done better. So the best time, definitely, The winner here has to be Christina because it's a further value away from 0. So Christina performed better, which is B. And the answer should be, yep, B. Normal probability plot. Now, I think for period 5, we haven't gone over this. The normal probability plot basically states that if it's linear, you have a normal distribution. And I've shown this to my period 4 class very briefly. On a stat plot, it's this last one. You can see how it kind of gives you a little bit of a line right there. So as long as you see a linear shape for normal probability distribution plot, you have what we call a normal distribution. Anything other than those two will be, anything other than those two will be considered to be not not normally distributed, basically. So for normal probability plot, suggest that normal its model is plausible is when a substantial linear pattern is present. So we'll go over this problem. I think there's one open-ended question that deals with this, so we'll go over that more in detail. Everything else you don't want to remember. Just always remember a linear pattern for a normal probability plot. That is when a normal distribution is going to occur. All right. Okay, so for number 6, for a normally distributed population, mean of 0, standard deviation of 1, a standard normal distribution, a population interquartile range. Now, the interquartile range is anywhere between the 25th to 75th percentile. So what I'm going to do is I'm going to go to my calculator. I'm going to go to my distribution, and then for the inverse norm, because I have the area, and I want to figure out with the mean and the standard deviation of 1. Tail, I'm going to always keep it to the left for those of you guys who actually do not have this option. So then what I get is negative 0.67. This way will give me my 25th percentile. I'm going to copy this inverse norm, and then I'm going to simply change it to 75th percent. And now that gives me positive 0.67 to the right. Now, this range will cover the interquartile range. So all I got to do is just double it, right? Because it's the same number twice. So the answer here should be C. For a normal distribution with mean of 100, standard deviation 10, 95th percentile. All right, so pretty much I'm going to do the same thing. Normal inverse norm, 0.95, 100, and that should be 10. And so that'll be 116, which is E. What is the value of an observation that is 93rd percentile in an approximately normal data set with mean? Let's do it again. So inverse norm, 0.93 this time with the mean of 86, standard deviation of 8. So that's 97.8, which is 98. So CEC, yep, there are all the correct answers here. All right, so let's do number 9. We have lobsters, only 3.25 inches or longer, with a mean standard deviations of 5.5 and a standard deviation of 2.25. Approximately what proportion of lobsters will have to be returned to the sea? Any lobster that's smaller than 3.25 must be returned to the sea. So we're talking about this right here. So what's the percent of all the lobsters that is less than 3.25? Well, if you actually do the math here, if the mean is 5.5, one standard deviation to the left, you subtract 2.25 from 5.5, you should actually get 3.25 for this one, which means that right there in the middle is 68%. This 1/2 of it should only amount to 16, because 16, 16, 68, they all got to add up to 100%. So number 9, yep, it should be A. Number 10 was a little tricky, but I think you guys just first have to take a look at this. Take some time to kind of digest in, and then try to kind of locate for me, where possibly the center may be. Now, we're talking about the average, and we're not talking about the median. So it might be a little bit difficult to do because you can't really cross these out anymore. Imagine you adding up all those numbers and divide by how many those numbers are. But it's clear as day that this distribution has the highest mean, because it's somewhere between 15 to 18. The rest of them don't even really compare to that. So diet B definitely needs to be the forefront runner of this, because we're talking about largest to smallest for this one. So if I had to pick out of the rest of them, diet C, look at how much of the 0 and 3s happen. That kind of gives me an idea that, okay, the average has to be somewhere a little bit closer to 0 to 3. Therefore, it's going to be very, very small. And so diet C has to be the last, which doesn't really help because AC, which is a typo, by the way, they have the same thing, and D, those are the only ones. It's either DA or AD. Now, if you take a look at diet D and diet A, which one do you think is going to have a higher average is the question. The higher average has to belong to diet A here. Why? Because you have so much more in frequency, in terms of frequency, the value between 6 to 18. And 6 to 18 for here, well, first of all, there is no 15 to 18 in this one. This is not in comparison as large in compared to diet A's, ranging from 6 to 18. There are a lot of numbers going from 0 to 6, which means the average for diet D has to be the smallest one. So the diet D, I mean, not the smallest, but in comparison with A and D, D has to be smaller. So it has to be D for this, which is, yep, that's the correct answer. Which of the following is closest to the upper quartile, which means we're looking at the top 70 or the top 25% or the 75th percentile for this. I'm just going to kind of jot down the best way I can, give or take 17, of all the frequencies I can see for this. What is that? Maybe 7, 8-ish? Okay, that's 5. So that's 15, that's 45, that's 60, that's 80, that's 97. So let's just give or take, we're looking at about 100 data sets because we estimated. So what that means is we're really looking at the 25th number from the right. That should give me my upper quartile range. Now, the 25th number from here is somewhere here, or maybe possibly between 30 to 35. But luckily, any number between 30 to 35 is not even listed here. So the clear winner is going to be 37, which is between 35 to 40. That should be my upper quartile range. A data set consists of 5 numbers. An unknown 5th number. Now, this could be 0, it could be negative, it could be positive. It never tells me any clues as to what this 5th number is. For these 5 data points, the following statistics can never be greater than 0. Okay, so if you plug in 0 for this, or if you plug in positive, or if you plug in negative number, there's one number that is going to be never greater than 0, which is the median here. If you think about it, if you plug in 0, the median is 0. 0 is never greater than 0. It's equal to each other. Negative number here means that now your median is negative 4.5, or it could be that new number if it's like negative 3, but that's not greater than 0. If it's a positive number, again, the same problem occurs. The median is still going to be 0. Therefore, 12 is going to be the median. This is chapter 1 material for number 13. The interquartile range is 7 times 1.5 gives you 10.5. Subtract and add, you get 92.5 for this. You get 64.5. Anything less than 64.5 is an outlier. Anything greater than 92.5 is also an outlier. Luckily, we do not have that problem on the upper side, but we do have a problem on the lower because 60 is less than 64.5. So data has at least one, okay, not on the high end, one outlier on the low end, no outliers on the higher end, so it should be D. Which of the following statement is true? It is impossible for a data set to have a standard deviation that is larger than the mean. That is absolutely true. The mean can be 0 and the standard deviation can be 1. I just have it. So 1, anything with 1, I'm eliminating. If two data sets have 2 different ranges, the data set with a larger range will always have the larger standard deviation. Now, somewhere in your maybe just experience wise, this is just not going to be true. And I'll show you an example of this. Okay, just because you have a higher range, you're going to have a higher standard deviation. Let's put that theory to the test. So let's say I put 1 and 10. And when you do that, it's going to just be 2 numbers with a range of 9. So then I do this 1, let's say 2, 5, 6, and then 11. So the range for list 2 should be higher. So does that make standard deviation for list 2 higher? Let's put that theory to the test. So then I do this. Now it seems like if I just do list 1, the standard deviation is 4.5. List 2, the standard deviation. So I'm going to change this to list 2. Okay, so standard deviation of this is 3.521. Now you can see that the standard deviation is heavily impacted by how many numbers there are as well, because the standard deviation is the distance from the mean from the center. If the mean is congested with a lot of variables, a lot of numbers in it, then the distance amongst the values themselves must also shrink. Just because the range is higher does not make the standard deviation to be higher. So 2 is not going to be true. So the really answer is C. The interquartile range of the data can never be larger than the range. I mean, that's pretty obvious for this one. So number 14, it should be C. All right, number 15. What we have here is we have the mean and the standard deviation. 50 observations are 47 and 10 respectively. A new data set form added 3 and subtracting 3. So when you add 3 and subtract 3, overall to the total it did not change much. So the mean will not change. When it says mean will be smaller or larger, we're going to eliminate C, D, and E. So the mean of the new data set will be equal. The mean of the data set will be equal, but the standard deviation. Now think about what happened. The lowest number got closer to the mean because it got added by 3. And the highest number got also pulled in towards the center by subtracting 3 and adding 3 from the low end. So it shrunk, which means the standard deviation will definitely change. It should be B. It should be smaller than the original standard deviation. Number 16. If you take a look at where these things are located, 180, 55, 20, and okay, well, give or take roughly, just eyeballing it, it seems like those spaces, the 25th percentile, 25% of each of these parts of the box plot, is about the same, which means they're going to be roughly symmetric or approximately symmetric. But we talked about the difference between the two. If it's normal, not only does it has to have a really nice bell curve, but it has to exactly follow the 68%, the 95%, the 99.7%, the empirical rule in order for this to happen. Now, this cannot be told just by looking at the box plot. Now, the box plot here, I told you the shape is not it's not determined clearly. However, we can make some conjectures based on how it's shaped. Obviously, if I give you something like this, then that is clearly skewed to the right. But if it's something like this, there's a good enough chance that this is going to be symmetrical. So 1 is definitely going to be true and 2 is not. So it's between A and E. The sample distribution is extremely skewed to the right. Again, you can't really tell that from box plots. A is the best answer for this one. 2 data sets have different variances. A constant K is added. If you add, the only thing that changes is the mean and the median. The center changes, but the spread doesn't change. If you're wondering about what variances are, variance is just simply standard deviation squared. So anytime when you see variances, you want to relate that into standard deviations. I know that when you are adding, only mean and median changes. So both the variances stays the same should be the correct answer, because adding something doesn't change anything. But when you multiply, the mean will multiply by K. The standard deviation will also increase by a factor of K, which is also, remain unchanged. So that was my fault. So it should have been B. The mean and the standard deviations will both change by a factor of K. That is changing both center as well as the variability. Both of them changes. So IQR, variances, standard deviation changes because it spreads, it multiplies, as well as the measurements of center, which is mean and median. Number 19, z-score is a measurement of standard deviation. So you're looking at D or E. Anything with percentages or dollars, you're going to eliminate because the 1.25 represents how many standard deviations you're moving. So if it's negative, it's below. So therefore, it should be E. Which of the following is not a property of our normal distributions? The distribution is symmetric. Well, we're talking about not, so that is definitely going to be true for this one. The distribution is centered at 0, not all the time. The standard one is always at 0 with the standard deviation of 1, of course, but that is not property of all distributions, so 2 has to be part of it. The mean and the medians are equal? Yes, absolutely. So the answer here should be B, because we're looking for the one that's not. The rest of the questions here are very, very simple. So they're all a bunch of calculator questions. I'm just going to type this away. So the mean is 90, and they give you the 96th percentile and the standard deviation. So first, let's do inverse norm, 0.96, with the mean of 90 and a standard deviation of 15. Oh. Yep, 116 and 21 is C, definitely. All right, so from 22 and onwards, I'm going to have to show you something a little bit different. So a variable is distribution at 100. About 10% of the time, the x takes on a value that is less than 80. So we have the mean, we have the value x, but they give you the p-value in terms of the probability, but it asks you for standard deviation, which is the sigma. So now how are you supposed to solve for something like this? Well, you have to use the z-score for this. Well, how do you get the z-score? When you go to distribution, when you do inverse norm, with the 10% that's provided, you're going to put that as the area. You're going to put the mean and the standard deviation as the standard value for the normal distributions, which is 0 and 1. When you type that in, that 0 and 1 for mean and standard deviation respectively, that will always give you your z-score. So the z-score here is negative 1.28. Now with that, you're going to use this formula, because this represents the z-score. So if you do the math here, the value is 80 minus 100 over standard deviation. So you take this negative 20 and divide by the z value that you got, and then what you're going to get is the answer is 15.6, because that's the standard deviation when you do 80 minus 100, because that's the value minus the mean, divided by the standard deviation that we found out. That gives you your z-score, which we figured out by using inverse norm of mean of 0 and standard deviation of 1. Where did that come from? The z-score, it doesn't matter what mean or standard deviation that you use. We use this for a reference guide because the standard deviation is not given. But when you use the standard normal distribution with the mean of 0 and standard deviation of 1, it's going to be fine as long as you have the percentage and they're asking for asking you for the standard deviation. This is what you got to do. They're all intertwined with each other. So feel free to use that. When they give you the percentile to find the z-scores, just use that and then you should be on your way. Number 23 is going to be the same problem. We're going to have 15%. So we are going to go to our calculator and then we do 0.15. Okay, so the z-score is negative 1.0364. And then we're going to use x, which is, I believe, 3, minus 2 over standard deviation here. Now, I think it's centered at 2 pounds that are larger than 3 pounds here. I see. So I think I got the wrong z-score because 15% of the fish in the lake are larger than 3 pounds, it says, which means that 15% is the higher end. So I have to actually go back here and then you have to 85 percentile, because then the rest of 15% will be on the top. 15%, that's what they're talking about. All you got to do is just change the z-score to positive. And so that's 1 divided by that answer, because that's 1, and you move the algebra around 1 divided by the answer. That should give you your standard deviation as 0.96 here. Suppose that the number of dandelions in 1 acre grassland plot is approximately normal, 750 and 80. Empirical roll, everybody. So 750. And I can just do a quick math here. 2 standard deviations means 160. So that gives me 590. And I'm pretty sure that 2 standard deviations to the right is 910. So D is the answer. Now, cumulative relative frequency means that overall, how much of the the time of day within the span of time, how much of the percentage is actually within those two boundaries. So for example, between 8:46 to 9 o'clock, that amounts to about 11% of the data. From 9:01 to 9:15, that's about 12% of the data. From 9:15 to 9:30, we have, that's like 334. I think we have a clear winner here. So that clearly triumphs over the rest, which should give you about 21 and 17 respectively. But this will give you the highest. Most likely to clock into work means the highest probability is what we're looking for. Okay, so we'll do 26 for the open-ended. Consider a study in which the heights of a very large sample of male high school seniors. Okay, so we have a mean and the standard deviation. What percent of heights in the sample will exceed 79? So that's 1, 2, 3 standard deviations away, and we're looking at that. If you do the math correctly, 100 minus 99.7 gives you about 0.3%. That means 0.3% left or right. So you have to divide that by 2, which gives you about 0.15% for the highest and the lowest. But, they only ask you for exceeding this, so that you just have to write one of those down. I think you should be okay. The empirical rule states this. I know the answer key that I provided for you says 0.135% by using I believe what they said was the normal CDF. It's gonna, like I said, both of these should be okay. I just wanted to do it quickly, so I use the empirical rule. What is the approximate percentile of a male senior who is 73 inches tall? Again, that's 70 to 73. That is 50% here, because the half of the lower than 70 would be 50, and the higher than 70 is 50, exactly cutting into 2. Then this part is 1/2 of the first empirical rule. So 68% is the first empirical rule, and when you take half of that, it gives you 34. So when you add on top of that, it gives you 84%. So 73 inches tall means that you're about 84th percentile. Now, if that was a little bit too theoretical, let's say that you want to rely on your calculator a little bit, and then you want to use, I'm sorry, not inverse norm. So normal CDF, the lower would be 0, because the height can never exceed, can never go below 0. 73 with the mean of 70 and a standard deviation of 3. And so there you go. The exact precise answer would be 84.13, but you get the idea. So empirical rule, normal CDF, they should give you the same thing. When the data were summarized, the value of the first quartile was written down, but then smudged. There's a general agreement that the writer meant to indicate 66 or 68. So the first quartile means 0.25. So let's use our calculator here. So inverse norm, 0.25, with the mean of 70 and a standard deviation of 3. So we're looking at 68 inches, and so therefore that should be the first quartile of the description of the question that's provided for us here. Now, because of the time limit, I'm going to stop here. There's going to be a part 2 video. It's going to be very short, which is going to go over the rest of them. Let's catch you guys later for part 2.